So these muddy points from last class, it seems that things are getting probably somewhat clearer. There were some concerns about, say, spherical acoustic assumptions. I'll talk about that. And particle velocity derivation, I will clarify some other aspects of it. The things that I derived, I will let it stand, and we'll see an example of that to make it more clear about what is happening. One person said that this anti-derivative approach felt like a shortcut. So we'll see that it's not really a shortcut. It is a formal solution approach. There's nothing more or nothing less to it. Okay. And the second part of the D'Alembert solution, as pointed out by this person, is just that we are saying that while for a plane wave, that is a 1D acoustics in plane in Cartesian coordinates, what we are doing is we are having some source which is making some oscillations that are planar. So otherwise there will be some variations in y and z also. So whatever oscillations or whatever fluctuations are happening in the medium are in the x direction, and because our domain is doubly infinite, it can go either left or right infinitely. So the solutions that we allow are both the left running and the right running waves. On the other hand, for the spherically symmetric problem, we are naturally choosing a particular coordinate system and then saying that my solution is spherically symmetric. So, so maybe I'll answer that question about what are the assumptions of spherically symmetric acoustics. So the usual assumptions are there, like linearized solution, inviscid, and in addition there is no base flow, so it's quiescent, and the density and velocity pressure are uniform. So those are all there. Plus now we are looking for a very particular solution. So you can ask me why. It turns out that this particular solution is relevant for us later on. Let me just say that. So the solution kind that we are looking for are of this form, that P prime should be a function of R and T only, which establishes a spherically symmetric part of it. Then if you substitute this pressure fluctuations in your governing equation, in the momentum equation, you notice that the velocity vector can only have R and T only, and this is UR prime, U theta prime, U phi prime in general. But because of the choice of the particular form of the pressure fluctuation, that it is only spherically symmetric, we get rid of these terms because those are trivially constant, if not zero. And we choose to call this as U prime because that's the only velocity component, scalar component, which is non-zero in our problem. Okay, so this is the so and apart from the assumptions of linearized inviscid acoustics and in a quiescent medium, the only other thing that we are saying here is that we are going to choose this form. We are going to choose to study if pressure solution were of this form, nothing else. If it is of this form, then what we are naturally saying is that the wave fronts, that's what this is coming out to be, wave fronts that is of are spherically symmetric. And so if they are to be spherically symmetric, then my source must be at the center of that sphere or all over the world. So if they are at the center of the sphere, then I've got outgoing waves, which is this, we found out f of r minus c naught t by r. If they are coming from everywhere else but is still maintaining that spherical symmetry, then they will be of this form. We saw that, but then this is physically impossible to have. So again, the universe is conspiring to send you a piece of information. That's not going to happen. So we are choosing to study this solution only. With this choice, we then went about seeking for a solution for this particle velocity. So again, if we choose to denote the solution using the outgoing wave, then we derive that u prime rt is f of r minus c naught t by rho naught c naught r. You will recognize that this is just the pressure fluctuation as you would expect, minus capital F of r minus c naught t by rho naught c naught r plus some constant term that we set to 0, and this f is the antiderivative. Where eta is the dummy integration variable and f is again the function of a single variable. So it's only backdoor entry if you think of this as you know the f and then you're doing something where we are this derivation doesn't know f. It is just saying it's any f, any function, linear, non-linear, I don't care. For such a solution, for pressure, we are trying to find the velocity fluctuation, and because of the nature of our equation, which is much not as simple as for the Cartesian 1D problem, we end up with this additional term which involves the antiderivative of the pressure fluctuations. So we'll see a bit more about that in a moment. But before we look at that, let us just study the physical nature of these two parts of the particle velocity fluctuation. So to do that, we will look at that this is our something that is creating this spherically symmetric wave. What we are going to do is we are going to choose to study the energy that is crossing a sphere of radius capital R. So the sphere of capital radius capital R, and that's a natural surface to look at for energy flux because it's a spherically symmetric problem. What other surface would make sense? So I want to understand the energy that is crossing that. So we have P prime is equal to f of r minus c naught t by r. We've got u prime equal to P prime by rho naught c naught minus this f of r minus c naught t by rho naught c naught r square. So we saw in the energetics development where we have derived this earlier. So now how do we find out the energy that is crossing this spherical surface? So you can look at the kinetic energy again, which will be half rho naught u prime square, and the potential energy will also be same as before because potential energy is a scalar quantity anyway, so it doesn't depend on the choice of the coordinate system. And so we had half of essentially so we had c naught square rho prime square by rho naught. So you can study again because you have got governing equations for these two, you can study what will happen to the total mechanical energy. So I will not go through a derivation, I invite you to look at that. But what you will find out is that the energy crossing sphere or spherical surface of radius r per unit time, of course. Sorry, if you have got pressure there, so I have written it in terms of density. In terms of density, I think this is what it is. So what might this be from your intuition? What was the notion of uh, power, acoustic power that is crossing a particular surface in the Cartesian 1D problem? Sound intensity, right? P prime U prime. So it turns out the same quantity holds. So acoustic intensity is still P prime U prime, and so this becomes, say, E is the total area, which is just 4 pi r square times the P prime U prime. And of course, you have to evaluate this at the R comma T. So please look at this, okay? It's not very difficult to get this following the derivation that we had for the energetics of a Cartesian acoustic wave in 1D. So if you look at this, then we have got 4 pi r square. So we'll leave that p prime rt for now, and this u prime rt we will write using this form that it is. There's part of it which is just p prime by rho naught c naught, and another part of it which is it was not there in the Cartesian problem. There's one r I've already just now, capital R square is capital R. So this is RT. So you've got 4 pi. So instead I'll write it in terms of the f function, which will make it clearer. Okay. So this is f of r minus c naught t by r, and this is also f of r minus c naught t by r. So then this r square cancels out with this r square, and so you've got f square r minus c naught t by rho naught c naught. But there is an extra r sitting there for the other term. So you've got 4 pi f of r minus c naught t, capital F of r minus c naught t by rho naught c naught r. So let's draw a little picture to clarify things. So suppose I were to draw in the same picture a notion of this waveform. So suppose I were on this particular surface, and on that surface, if I were to just plot here what the p prime is versus r at a particular instant of time, then it might look something like, say, some pulse like that. So by the time this would have gone here, it would have done what? Can you sketch what that pulse will look like? Maybe I'll just plot versus t. T will make more sense. So at this particular location, I want p prime versus t. Then what will, I've given you p prime versus t, then what will p prime versus t look like at this point? Based on based on what we have given as the solution already. Just like so, I plotted p prime versus t at a smaller radius. I want to get a sense of what is p prime versus t at a higher radius. So most of you are getting it right, that it will be squished. So at this location, let's call it r prime. So if this were r prime and this is a larger radius r, then the amplitude must decay as 1 by r, and so I must get a lower radius. The additional wrinkle is that it will also appear at a later time. You have to shift it and draw a smaller. If this were t equal to 0, then it must have shifted, or means must only arrive at a later time. It will take some time to arrive there also. And that, of course, the shift is very exactly equal to the c naught and the excess distance that it is to cover. So p prime versus t, you have to tell at which radius you are plotting it, right? So I am plotting this one at this r prime radius, and this plot is at the r radius. So this is my notion of the p prime, and the shape of this wave, this particular squiggle that I drew, that shape is governed by this f function. And suppose it's got some amplitude. That amplitude is not changing. It's just the f function. It's not changing. That's the essence of this f function. That the function is same, only the argument to it is different. So because this function is not changing, irrespective of where I evaluate it, even for any r, this energy that is crossing that particular sphere is not dependent on r. When you are getting that signal is of course different. So at which time you will have a particular, when this wave will pass over you is of course going to be different. But that is not going to change the amplitude of this f square. So the energy that is crossing this particular sphere of radius r is, at least from this first part, is independent of r. So the same energy is conserved, and that is the essence of acoustics. So this is are agreeing with what we also had in the Cartesian 1D. So this we'll call the acoustic part or the propagative part. It propagates, it doesn't suffer any losses, barring of course viscous effects. We had neglected viscous effects. In viscous medium, of course, it will dissipate after some time. But here, if we neglect that, then this is purely propagative, never suffers any change in the energy that it is carrying. Of course, you have to integrate the energy over the larger and larger sphere, but what else can you do? This one, on the other hand, f is again of particular amplitude. Its antiderivative, capital F, is another function of a particular amplitude. So the numerator is of a particular amplitude independent of r, but there is a 1 by r sitting in the denominator. So this one decays. So it's what is called, through some quirk of naming, it's called hydrodynamic part. Nothing to do with water, but that's the nomenclature that has stuck. So a lot of time we are going to look at acoustic versus hydrodynamic components of a solution. So I'll let it be a question to you all, to think through, where did this energy go? So think about it. We'll touch upon that a bit in few minutes, but think about it. So another thing that is called is reactive as opposed to propagative, and again we will see the reason for that in a moment. So this part, the other part that we are discovering. So again, we took a pressure fluctuation which satisfies the spherically symmetric wave equation. So everything is nice and beautiful. We think that it is all acoustic, but it turns out that if you use the other parts of the fluid dynamics equation, which of course governs the particle velocity, then the particle velocity corresponding to that choice of pressure fluctuation has got two parts. It's not purely acoustic, because again, this is our choice of the nomenclature, is that it is what doesn't suffer decay in propagation is what we call acoustic. It's our nomenclature. There's nothing intrinsic about this part or that part. These are just parts of the solution. It's our uh, uh, our motivation to give things a name so that we can discuss about them, that makes this be termed as acoustic or propagative, and the rest of it we just call by exclusion hydrodynamic. So let's have a bit more sense of what is going on by now choosing what we did for the Cartesian thing also, in looking at a harmonic solution. And this is again very relevant for us from your homework also. We see that the spectral analysis is a very beautiful tool. Why is it such a beautiful tool here? Why suppose for fluid dynamics, why don't you do so much of spectral analysis? Here also we have got a very non-periodic, your signal that you are dealing with is not really periodic. So I'll let you think about that, but I'll again propose a harmonic solution, and then we'll see what for the pressure, and then we'll see what this all equations, and we'll have a specific small f and a specific corresponding capital F, which will hopefully make things more definite. So harmonic solution. So in line with what we did before, and with the abuse of notation that you are now willing to agree to, we choose I omega t minus r by c naught by as the proposed solution. Again, it has got the r minus c naught t argument, or t minus r by c naught argument, and we are keeping this a complex amplitude, as constant. Okay, so this is a constant independent of time or radius, and we are incorporating that 1 by r factor separately. So you'll remember that this agrees with our f minus r minus c naught t by r form of the solution that we found as a general solution from D'Alembertian analysis. So given this form, we can do two things. I can use u prime r t is equal to f of r minus c naught t by rho naught c naught r minus f minus r again f j is the antiderivative. Or I can start from scratch and use the momentum equation to get the pressure. Okay. So in my notes I have given you the second form, that is the second approach, where given this pressure fluctuation, which is now very definite, I am integrating the momentum equation again, and then we are avoiding this F notation, okay, which is probably troubling for some of you. But here, because one of you raised the discomfort with this capital F notation, I'm going to use that. Okay, and persist with that and see that you'll end up with the same answer. Of course, you'll work out. Okay, so given that this is F, so I want you to write down this F function for this particular choice. What is F? So F of eta is what? Write it down. What is F of eta given this particular form that we have chosen and this particular form, which are equal? What must F be? So it's a e to the power minus I omega eta by c naught, not by r. So that is F. Then I'm invited to integrate that. Capital F of xi is 0 to xi f of eta d eta. A comes out e to the power minus I omega eta by c naught d eta. A by minus I omega by c naught to the power minus I omega zeta by c naught minus A by minus I omega c naught e to the power 0 is 1. So we subsume this part in our constant term again, because that is constant, and so we can write this as just I'll multiply I on the numerator, so it's I A by omega I A c naught by omega e to the power minus I omega xi by c naught. So now I'll substitute in u prime. So u prime RT is f of r minus c naught t is just the same form, of course, a to the power I omega t minus r by c naught by r, and rho naught c naught is the extra term that comes out, this rho naught c naught r. So f of eta is just this quantity, and the capital F I just obtained that. So this is now minus I, or maybe I'll just keep it as it is. So a by minus I omega by c naught to the power I omega t minus r by c naught by rho naught c naught r square. So if I multiply and divide by minus I, then this becomes still minus 1. So I have to multiply and divide by I. So it doesn't matter. So I'm not using that form. So just focus on this. So my goal is to attain a notion of this acoustic impedance. So some proportionality between the particle velocity and the pressure fluctuation at a particular location and at a time. So in pursuit of that, I know that this part is pressure fluctuation, and I'm getting the same part here, the same part out here, say for an extra r squared term. So I keep that common, that is the pressure fluctuation, so P prime RT, and I get a rho naught C naught, so I'll keep that also as common, and so I've got a 1 minus 1 by minus I omega r by C naught. Yeah, so I can write this also as, can take the I in the numerator. So this is the form. If you are so inclined, you can think of this as a complex quantity. It is a complex quantity. There is a real number. This C naught by omega r is also a real number. So there is an extra I there. Okay. So we can actually write it as the amplitude of that complex quantity, which is root over 1 plus C naught by omega r square, P prime R T minus some phi, just bear with me, where phi is the phase tan inverse of this quantity. So C naught by omega R. So again, this you can do at home. It's not very particularly relevant. But what is mainly what we are seeing is that the acoustic impedance, which is the proportionality between U prime and P prime, is not just rho naught C naught anymore, but there is an extra term which is a function of frequency and the radius where you are, and what is the frequency of the wave that you are considering. So the amplitude depends on that, and as does the phase of it. The phase is also a function of omega and r. C naught is a medium really constant. As I said, the nice things about the 1D acoustic Cartesian acoustics were that everything was clean, and the acoustic impedance came out to be just rho naught C naught. Here it is a more complicated relation, and of course it is complex. This is a complex number. So this is a complex quantity, and that gives you a complex impedance. That's the nature of the problem. To get a bit more sense of this acoustic and hydrodynamic part, what I'm now going to do is specialize this for small and large r. So what is small r to you? How small is small? 1 centimeter? 1 millimeter? So what is the relative scale? Wavelength. So that is coming out very clearly. C naught by omega is the wavelength. So you have to specialize this for small values of C naught by omega and large values of C naught by omega. That is small values of lambda by r and large values of lambda by r. So let's do that. So I'll just write out our solution again. 1 minus I C naught by omega r P prime r. So for large or let's say distant observers. So again, distant has to be that r is much greater than lambda, which you will remember is 2 pi C naught by f, which is C naught by omega into 2 pi, omega by 2 pi. So for r much greater than C naught by omega, we have got lambda by r or C naught by omega r is much smaller than 1. What did I do wrong? Much smaller than 1. So u prime rt can be approximated. So this becomes a very small quantity compared to 1, and so this becomes equal to I'm missing a p rho naught C naught. And I get my favorite Cartesian result, that the acoustic impedance is just a constant rho naught C naught. So if you are far enough away from this source, whatever is creating these acoustic disturbances, suppose I am so far out, at your location, depending on what is the lambda, if you are far enough relative to lambda, then whatever particle velocity fluctuations will happen will agree with whatever pressure fluctuation, acoustic pressure fluctuations are occurring, and this constant of proportionality is a constant really. For what is called near field observers, r is much smaller compared to the acoustic wavelength. So which means that C naught by omega r is much greater than 1. We have that u prime rt is equal to or approximately equal to minus I C naught by omega r P prime rt by rho naught C naught. So the acoustic impedance is rho naught C naught omega r by I C naught minus, and that of course is strongly dependent on omega and r wherever you are and what frequency of wave you are looking at. So the acoustic impedance depends on all those details now. Whereas in the far field, very distant observers, the acoustic impedance is constant. So it's a nice problem that, and we recover essentially the Cartesian coordinates, barring that 1 by r factor. So 1 by r decays there, which is what you have in your intuition as a spherically symmetric acoustic wave, that there's a decay in the amplitude to preserve the energy that is being sent out, and we saw that the energy preservation part of it. And only thing is that, and it behaves essentially locally as a plane wave. So you are, the wavelength is like this. If you are very far away from that, then locally the wave is essentially plane. Amplitude is decaying as 1 by r still, but the shape of the wave is essentially locally plane. Whereas when you are very close, then things are very different. Okay? Then things are much more complicated. So if you study this now, so this is e to the power, or so I can write this as e to the power minus I pi by 2, that is minus I e to the power minus I pi by 2. Pressure fluctuation, remember, was I omega T minus R by C naught A by, so rho naught C naught omega R square by C naught. So I've just taken out C naught omega, everything is here, this quantity is here, and that minus I am writing as e to the power minus I pi by 2. Okay. You will recognize this is e to the power minus I pi by 2 is cos pi by 2 minus I sin pi by 2, and so it is minus I, because cos pi by 2 is 0. So I can subsume this minus I pi by 2 inside this other part of the exponential, have all of this together. I don't want to look at that right now. I. So what we are finding is that whatever the pressure fluctuations are doing now, my particle velocity fluctuation in the near field is lagging it by pi by 2. So whatever the pressure fluctuations are doing now, the particle velocity will have the same behavior, but after pi by 2 phase. Okay. And that is where the notion of reactiveness comes from. It reacts to the pressure fluctuation, this part of it. So not very surprisingly, you can relate these two parts or these two specializations to what we also have earlier as f of r minus c naught t by rho naught c naught r minus capital F of r minus c naught t by rho naught c naught r square. So this was the acoustic part. It didn't have any change in energy as it propagated out, whereas this was what we call the hydrodynamic part, and this also has got this reactive nature. And of course in the near field, this is the one that dominates because there is 1 by r square, which is much stronger than 1 by r for very small r, whereas in the far field this 1 by r square is much smaller compared to this 1 by r, and so this is the one that dominates. So this is the one that we found to be this part was p prime by rho naught c naught, and this one we found as this part, which is the reactive part, which has got this reactive term to it. It actually goes back to his question about where did the energy go. So I like you to think about it a bit more, about what is happening in the near field, whether we are actually capturing all of that physics correctly, whether our model is correct in the near field. So think about that. So from there you can probably answer about what is happening to the energy. Maybe our model is not correct. Maybe we have neglected things which we should have retained in the near field. Think about what is happening in the near field. Think about the near field. You will see that there is a problem in our model itself, near field. So these are the results that you get once you have chosen this model that we have, and that has led us here. Now I'm asking you to question some of those assumptions at its root to see whether you can understand some of these things. Yes. What is invalid? Linearization, of course, not there. It's not linear. So all our entire model was linear. That entire falls apart. So this was all derived using that linearity. Only in that sense does all of this get mathematically derived. But the physics are questionable in the near field. If you are thinking of that energy as going somewhere, yes, you are correct. Uh, so I'll again point you back to that linearization assumption. So in our linearized assumption, there is what we have considered, and there are other things that are also linear but are decoupled by superposition. So there are other phenomena that are going on. I'm not saying that nothing is L other than our solution. But in the linear world, they all don't talk to each other. They are not affected by each other directly. So in that sense, there is a hydrodynamic part which is carrying energy. But we can consider an acoustic part of your solution as if it's living in its own world. And it is having our usual notions of energy preservation. So there's a spherically symmetric wave such that at a distance of 1 meter from 100 hertz source in air, pressure fluctuation amplitude is 1 Pascal. So you're asked to find out U prime at r equal to 1 centimeter and characterize that for all time. So P prime is again equal to A into e to the power I omega t minus r minus c naught by r. So substitute and then figure out what is the only unknown. What is unknown? So because it is harmonic, our form still prevails. So what is unknown here? Huh? A, right? So we are saying that at I omega t minus 1 meter by c naught by 1 meter, this is equal to 1 Pascal. It's amplitude. Take the amplitude. So A is equal to 1 Pascal meter. So with that in the bag, now we recall that U prime R t was that root over 1 plus C naught by omega R whole square T prime R t by rho naught C naught phi by omega. So yes, there is a phase lag. If you are just interested in the amplitude, then you just have to calculate this quantity. So C naught is 340 meter per second for air at standard atmosphere. Omega is 2 pi f is equal to 2 pi into 100 hertz. R is asked to be 0.01 meter. Rho naught again is 1.225 kg per meter cube. Pressure amplitude you can find out at 0.01 meter as 100 Pascal. So P prime R equal to 0.01 T amplitude is 100 Pascals. It's 100 times closer to the source. So it goes as 1 by R. So you can figure out then that the amplitude of U prime RT is 13.3 meter per second. So we will evaluate whatever the pressure fluctuation is there, and it will have the phase lag. Uh, so two reasons why we are not considering here. We are just interested in the magnitude of this thing, so the phase will not matter. And the other part is that so the phase will affect this part of it. Yeah, true. So, but if you are just interested in the magnitude, and it's a sinusoid, amplitude was given. So, oops. So So find out the amplitude of u prime r. So this harmonic analysis that you are again doing for your homework, I hope you see the relevance of that. Because it's all linear, because our acoustics is linear, we can think of each of these harmonic terms, each of these sinusoidal waves of different frequencies as living in their own worlds. They don't talk to each other. They are all going on their own merry way, and we can study each of them separately. And we are finding, yes, that the acoustic impedance does depend on the frequency. So it is not as clean as in the 1D Cartesian case, where it was much cleaner. But here it does depend on the frequency, but we can get a sense of what is happening if we look at each frequency separately, as opposed to that more complicated capital F form, which was confusing to some of you, that antiderivative form, which is not very clear about what is going on. So we'll get another sense of the power of this notion now that you have come across this. So I said that we are going to end with an open air theater example. So suppose that at an open air concert, the sound radiated from an arrangement of speakers generates an overall sound pressure level. So we talked about overall sound pressure level, I hope you remember that. So OASPL of 110 dB, very loud, at a distance of 20 meters. What is the mean power output? For acoustic power output, mean power output from the speakers. Assume, okay, I'll let you figure out what assumption has to be made, and I'll articulate that. So most of you have got started off well. So we're just recalling the definition of OASPL. So you've got 110 equal to 20 log 10 of PRMS prime by 2E5 minus 5. So 20 micropascal. So that should give you a PRMS of 6.32 pascals. So it helps to draw a sketch of our open air theater. So here is the little loudspeaker, and here is somebody, say, on an upper tier. So that distance is 20 meters. So there is some wave that this guy received, and we have to figure out what is the power that the speaker sent out. So what do we do? 4 pi r square. So what did you assume there? That is the assumption. What you are assuming is that the grounds are not reflecting, because there is a direct path and there is also a ground path. You are assuming that the grounds are absorbing. So that is the assumption that we have to write. Assume that all waves incident on the ground are absorbed, and that the sound field is omnidirectional. So that you have already said. The sound field is spherically symmetric. So with that, indeed, you are right to say that the power that the speaker sent out must be equal to 4 pi r square into p prime r u prime. So power is equal to 4 pi r square into p prime u prime. And what else? So these are still primes, these are instantaneous fluctuations. How do you get a notion of a power? RMS value. So we'll do an RMS of this. So RMS power is what I'm asking for implicitly. So P, assume that we are in the acoustic far field in writing u prime as p prime by rho naught c naught. So this is the instantaneous power that this acoustic loudspeaker is throwing out, and so I'll get an average power, that is what is asked for, average power output is P bar say is equal to 4 pi r square by rho naught c naught integral 0 to t p prime square 1 by t dt. So I'll take an average over time and for limit t tending to infinity. Then what do we do? This is the PRMS. This is the PRMS square. So this is just 4 pi r square by rho naught c naught into P RMS square. This comes out to be some 492.8 watts. If you substitute that 6, so here we are not assuming it's a sinusoid. It's an arbitrary signal. Of course, you would not go to a concert to hear a sinusoid. So it's an arbitrary signal, and which is fine, right? So you have got a PRMS notion, which is giving us a very nice way of estimating the average power of the speaker. This is all that I wanted to discuss about nice 1D acoustics. So next we'll be getting into the general problem. So we'll talk about 3D, is general perturbations. I should hasten to add still linear. So what we'll start from is compressible Navier-Stokes equation, and we'll start throwing one phenomena away to get to where we want to. Okay? And hopefully in the process of throwing away things, you will recognize what is acoustics as a matter of exclusion. As a matter of elimination, we'll come to what is the essence of acoustics by starting from again the basic fluid mechanics of Navier-Stokes equations. We'll also see that our nice things that we looked at, that is the 1D Cartesian and 1D spherically symmetric solution, they are also special solutions of the same equation. And so that way there is, so we did not leave out any physics in that problem, we only left out the general solutions that are possible. And we'll also get a sense of when those specialized solutions are relevant, when we can expect to encounter them. So of course, you have to start from the conservation equations for viscous compressible fluid, which is a compressible Navier-Stokes equations. So unlike the usual form which we'll just now write, we'll add a certain extra thing to it. Okay, right now it will make no sense. It will seem to be violating all the nice conservations that we hold dear, but we'll make use of that later on. For now, just humor me. So the mass equation is again del rho del t plus u dot grad rho plus rho grad dot u. So that is equal to 0 for the general problem, but I am going to generalize it further and add a rho q to it on the right hand side. So this q deserves some discussion, very brief discussion now, but we'll make great use of this Q soon. Okay. So this Q is called the volumetric source term. Volumetric in the sense that this left hand side gives you a sense of what quantity are we conserving here, left hand side, mass. So we have multiplied or dividing through by rho, we get a sense of the additional volume of fluid that we are adding or subtracting from the flow, which we should not be allowed to do based on conservation of mass, but we are keeping that for later use. Okay, for now just treat it as some non-physical mathematical extra term that I'm keeping. Similarly, the momentum equation, I'll also leave some extra term. So that I'll write in the, so this is the convective form or the non-conservative form of the equations. So this part you should be very familiar with. This is the convective acceleration. Yeah, I'm going to subsume that in this F. This is not our regular body force, that is the gravity. This is again an extra source term. So that F is the force source. It's a vector term. So we are going to call whatever stays over as the force source. So this tau is the viscous stress tensor, which by Stokes hypothesis, if you do not recall these things, no worries, because we are going to chuck them anyway. We are just going to make it an inviscid, this entire course is on inviscid flow. But just for completeness, I am just noting it at one point so that we are aware of what we chucked out. There is a tensor, second order tensor. So in my notation, one single underline is a first order tensor or a vector, and two underlines is second order tensor, or a, if you want in a matrix, but it's not matrix, it's a tensor. So what is this I? Identity matrix, so identity tensor, and this part is the additional dilatation part that comes in the compressible flow. This is the gradient of the vector, it's a tensor, and this is its transpose. So this is the symmetric part of the viscous stress tensor. Then the energy, given that later on we are going to use inviscid analysis, we can write the equation in terms of the entropy again. So this equation may not be familiar to you. I suggest if you are interested in looking at where these things come from, or how you can derive these from your other knowledge of energy equations, then you can look at Anderson's, one of the many books he has written, Anderson's textbook on CFD. So he has written a computational fluid dynamics book. In that, in the appendix, he has derived all these equations very nicely. In the appendix, or there is a separate chapter on equations. Okay. So there you will find this form. Again, the convection of entropy. So this S tilde is an energy source. I'm going to remove that tilde soon. Okay. H is the conduction heat flux vector, which by fixed law is given by this. So this is fixed law. This is Stokes hypothesis. S is an yeah, energy source term, or some this is the entropy, small s. This is an extra term that we are including in the energy equation, or retaining in the energy equation. So I think I'll stop here, let you write out what is not clear to you, with the hope that you're going to go back and just look at the derivations for this. Again, we are not going to test you on what is this tau later on in a quiz. I'm not going to do that. But at least these forms of the equations you should be comfortable in understanding where it came from. Okay.